Active Relay School Plus webinar series. Today's session is about Transformers protection. My name is Monica Gevorgian, and I'm the moderator for today's call. First, whether you are working from home, from an office, or factory, we hope that you and your families are safe, healthy, and you are practicing good measures to remain so. Before we get started, I'd like to go over a few housekeeping items. Please refer to the Q&A widget to submit any questions that you have during our presentation. We will address as many questions as possible during the webcast, and if any questions is not answered, we will send out answers as a follow-up. You have an opportunity to receive your certificate after 40 minutes from the start of our webinar, and please download your exclusive certificate right from the presentation deck through the widget located on the right side of your screen. Keep in mind that this presentation is being recorded and it will be shared following the broadcast. Moving on to some technical issues. Since some of you may be working from home, we expect a few more technical issues than normal. If you have any audio or visual difficulties, please pay attention to the following tips so that you have the best experience today. First, close all other applications and internet browser tabs to increase your bandwidth. You can also try to logging out from your VPN, which tends to slow down your operating speed, as well as switching to the Google Chrome browser if available to you. Second best option for browser will be the Microsoft Edge. Moving forward, I would like to introduce our speaker today. Our presenter today is Mike Cockett, Senior Application Specialist at Hitachi ABB. Mike will be available at the end of the presentation to answer your burning questions. Thank you and enjoy the webinar. Mike?
Thank you, Monica. Hi, everybody. It's good afternoon for me, but for others it may be good morning or good evening. So thank you for joining the webinar. To start off then, just to have a quick look at the presentation overview. So what we're going to do is we're going to look at transformer differential protection, or 87T, principle of operation. And this is really as more of an introduction. So when I get into the later topics, which is really the theme of the webinar, we will have this as a basis to work from. So the two topics really that we're going to be focusing on is the selection of the phase reference side, and this will become more clear as we go through the presentation, as well as the impact of the restraint current calculation method. And then we'll just end off with a slide of conclusion. So just to start, I have a quick poll question, and so I'll hand over to Monica to do that.
Thank you, Mike. Hello again, everyone. So you have an opportunity to answer our poll question. Please choose the best option applicable to you. You will have 15 seconds to submit your answer. Thank you. Thank you all for your answers. Dear Mike, here we go with the poll results. Please see the results on your screen. Thank you.
Okay, well, thanks for answering that, everybody. So I see less than 30% are aware and understand. So that's great. That gives me more than 70% who would hopefully be able to choose the first option by the end of the webinar. Okay, so as I said, well, firstly, when we look at protection application in that the utilities do, very often they require, if they're going to have two main protections, or a system A and a system B, they require that these relays come from different manufacturers. And they have the reasons for that to eliminate common mode of failure, etc. So if you're now talking about protecting a transformer, okay, common expectations on the part of the protection engineer that is applying the now two different transformer protection relays from the two different manufacturers could be that they have the same settings. Okay, it's the same transformer, so the expectation could be that these two relays should have the same settings, that they should operate identically, and in fact, if they operate, they should, and if they operate correctly, they should report the same target indications for the same fault. So that, I believe, is what could be common expectation from the utility protection engineer who's applying the transformer protection relays. So as I said, we will start by just having a look at the principle of operation. So here I show a transformer. The high side I will be calling winding 1, mostly from here on in, and the low side winding 2. Now when we're looking at protecting transformers, okay, with 87T or transformer differential protection, there are a number of factors to consider, okay, and these generally are the transformer or the turns ratio, okay, because the voltage on the winding 1 and winding 2 side is different, and so the current, for balanced current flow, the current flowing into the one winding and flowing out from the other winding has not the same magnitude. We need to look at the winding type, and here we're talking about whether it's a delta connected winding or whether it's a Y connected winding. We're talking about vector group, okay, and so this is really what is giving the phase difference between the currents coming in on the one side and the currents exiting on the other side, and whether zero sequence current can flow in the measurement circuit on the one side where it cannot flow on the other. So what is the solution to all of this? Well, firstly, it's to bring all current magnitudes to the same magnitude reference, and we call that the magnitude compensation. And then what we do is we align all current phase angles to what we're going to call the phase reference. So all have to be aligned to the same phase reference. And this is what is the angle compensation, phase angle compensation. So the phase reference side, there would be no rotation of current. So the current that is flowing in the primary network, it would be the same phase of current that would basically be entered into the 87T function. The non-phase reference side, those currents need to be then turned or rotated to align with the phase reference side currents. And also we need to eliminate the zero sequence currents, which, as I said just now, can potentially flow on one side only. So we're going to start off and look at pre-microprocessor-based relays. And we're going to look at the magnitude compensation and the phase angle compensation. So considering first the magnitude compensation, this was really done by CT ratios. So the CT ratios were chosen to give us best matching secondary currents. And for what the CT ratios couldn't do, then we had the relay tap selections. And for the phase angle compensation, this was primarily achieved by the CT secondary connection to the relay. So if we look at this example where I have a DYN1 or a DABY, depending which, I guess, which side of the Atlantic you are to how you would reference the transformer connection. But in this particular case, you can see that the current on the winding 2 side, and it's a delta Y transformer, and the current on the winding 2 side lags the current on the winding 1 side by 30 degrees. And just for a note here, so we understand the referencing, is that if winding 2 lags winding 1, then that's a negative angle, and which means that if winding 1 were to be the phase reference, that the winding 2 currents in this particular case would need to have a positive rotation anti-clockwise of 30 degrees to align with the winding 1 phase reference. Okay, so, and then if you look at the picture on the right, you'll see what was typically done for pre-microprocessor-based delta Y transformers, and you can see from this that the delta side was the chosen phase reference, because with the Y connection of the CTs, okay, there's no change or rotation of the phase angle from the primary current flowing into the transformer to the secondary current that would be connected to the protection relay. But if you look at the Y side, you can see there you have a delta connection, and that delta connection of CTs is the same as the delta connection of the actual transformer. And what that does then is it will rotate the current. So if you look at the output from the delta connection of the CTs, the current that would be connected to the relay, okay, that would have its phase rotated by the required angle. In this case, it would be, because it's a DY1 transformer, would be anti-clockwise 30 degrees to align with the phase reference side. And also that delta connection of the CTs would trap any zero sequence current, because if you had a ground fault on the Y side, okay, you could get zero sequence current that would flow. Now that zero sequence current would not be transformed to the measuring CTs on the delta side, because that zero sequence current would merely circulate in the delta winding. And so this delta connection of the CTs on the Y side traps that zero sequence current, and so removes it. So you don't have the problem of the 2 currents, one from each side, going into the measurement, where one is got zero sequence and the other one not. So let's have a look then at a balanced load condition. Okay, so I just made a calculation with some transformer size, and so you can see the winding 1 currents, and because it's a transformer that is shifting the phase by 30 degrees, you'll see the currents coming out on the winding 2 side, flowing on the winding 2 side, are then shifted by 30 degrees. So with the Y connection of the CTs on the delta side, you can see then that if you divide by the CT ratio such that you get the secondary currents, they will have the same phase as the primary currents, and hence they are really the phase reference side. Whereas if you look at the currents after the delta connection, okay, on the Y side, that delta connection is, as I said, shifting or phase rotating that 30 degrees, and so these currents that would flow out of the CT connection, delta connection on the winding 2 side, would now be aligned. Okay. Then the one thing to remember, and this has really got to do with reference direction that the relays work on, is that on the high side, balanced load flow, it would be current flow towards the transformer, whereas on the winding 2 side, it would be current flow away from the transformer. So actually, for the way the relay would see this is okay, we would need to see those currents because they're flowing away from the transformer as being shifted by 180 degrees. And then if we apply the tap, okay, I just made it a perfect tap on each side that would give you 1 per unit. You can see that the current flowing in on the winding 1 side, if you sum that with the current flowing out on the winding 2 side, the differential current in each phase would sum to 0. All right, so what can we say then about these pre-microprocessor relays is firstly that the delta side served as the phase reference for delta Y transformers, okay, because the CT secondary had Y connection. The CT secondary delta connection on the Y side served 2 purposes, and I've already mentioned what they are. Firstly, that they rotated the Y side currents to align with the delta side phase reference currents, and they also trapped the 0 sequence. Okay, so what they did, they eliminated the Y side 0 sequence currents from the differential measurement because 0 sequence currents are not flowing on the winding 1 or the delta side, and so you want to eliminate this 0 sequence mismatch in the calculated differential currents. So if we go now to microprocessor-based relays, which is where we are today, there you can see we have a matrix equation now that is handling all of this. And so that's the first point. And the second point is that now the CTs, because everything is handled in the matrix equation, okay, now the CTs on both the delta and the Y side can be directly Y connected to the relay. So looking a bit more into the matrix equation, okay, so we have these 2 matrices, the A and the B matrix, A on winding 1 and B on winding 2. They 3x3 matrices, and the elements of these matrices depend on the winding connection type. In other words, is it a Y winding or a delta winding? It depends on the transformer vector group. Okay, so remember the vector group is actually what is really giving you the phase difference from one winding to the next. And also the elements depend on whether the subtraction or elimination of 0 sequence current is enabled or not. Just a point to note now is when we look at these matrix equations, all quantities that I will show here are primary values, okay? So IA winding 1, IB winding 1, IC winding 1, for instance, are the actual primary currents flowing A, B, and C on winding 1 side. And then you can see in the equation there, B rated winding 2 to V rated winding 1. That will be the rated winding 2 voltage primary and the rated winding 1 voltage primary. And that ratio is what converts the current magnitude on the winding 2 side to the magnitude compensation or conversion to convert those currents to winding 1 side current values. Okay, so when we perform this this matrix calculation, we get some quantities, okay, and different vendors may call these quantities differently, but in this presentation, I will call them DCCA for winding, and DCCA and B and C for winding 1, and DCCA, B, and C for winding 2. And these values are what come out of the calculation when you do the matrix multiplication. And in fact, a term you may have heard before for these values is that they're commonly called the compensated currents. and how you would then get the differential current. So if you're looking at the differential current for phase A, it would be the DCCA winding 1 plus DCCA winding 2. And for phase B and phase C, it would be similar for winding 1 plus winding 2 for B phase and winding 1 plus winding 2 for C phase. So as I said, this voltage ratio, that is really your magnitude compensation, and that is what converts the winding 2 current level to a winding 1 current level. So because if you're going to sum two values, you have to bring them to some common level, because as I said, for a transformer, normally current going in on the high side and current coming out on the low side, for a perfectly balanced load flow, those currents are not going to have the same magnitude. So if you want to be able to sum them, you need to convert one of the currents to be equivalent magnitude to the other. And then, of course, the phase angle compensation. Okay, so remember that the phase reference side, so whichever that is, the high or winding 1 side or the low or winding 2 side, whichever side is the phase reference side, matrix multiplication must not introduce any phase shift. And then for the other sides of the transformer, which are then the non-phase reference sides, so the matrix multiplication on those sides must introduce a phase shift in the currents, such that the non-phase reference side currents are shifted in phase to align with the phase reference side currents. And we saw that with the delta connection for the pre-microprocessor based relays, where that CT secondary delta connection was actually performing that phase rotation to align with the delta side of the transformer, which was with the direct Y-connected CTs, was the phase reference. So this must do exactly the same. And the matrix multiplication must comply with the above, as well as subtract zero sequence component if required or if set to do so. Okay. So let's have a look here. Here we have, let's say we're protecting a transformer in service, and it has two microprocessor relays A and B, and relay A is set with the delta side as the phase reference. So as I said, it's a delta Y transformer, and relay B is set with the Y side as phase reference. If we have an internal single phase fault, you will see relay A that had the delta side as phase reference, that will operate in two phases. Okay, so you can see here we get the 87T trip, and we get operation in phase A, and in this case phase C. But for the other relay, okay, the relay that had the Y side as phase reference, now we've operated in all three phases. Okay, so the 87T tells you you've had that 87T operation, and it tells you it's been in all three phases. And the important thing to take away from this is both relays operated correctly. Okay, so what we're really going to do now for the next part of the presentation is to look at how this came about. So this is the typical characteristic for an 87T function. And along the x-axis, we have the restraint current. And up the y-axis, we have the measured differential current. Now, this is where we start seeing some differences, because microprocessor-based 87T functions from different manufacturers, they calculate different restraint current values. So for exactly the same fault, okay, one relay versus another may not put you at the same place on the x-axis. Okay. And for internal faults, okay, they can calculate different differential values. Okay, so what that means then is that even where you get located on the y-axis would be different for the same fault. And so now you have two relays, okay, which is calculating restraint and differential quantities differently, and then they apply it to a characteristic. And of course, if the point is above the characteristic, that would be in the operate region, and if the point is below the characteristic, that would be in the restraint region. So these are the kind of rules that you may be faced with. If a delta winding exists, select the delta side as the phase reference side. Okay, so if it's a delta Y transformer, then the phase reference should be the winding 1 side. If it's a Y delta transformer, then you should select the winding 2 side. Okay, and then of course for the other windings you would have to select the appropriate matrices. And if no delta winding exists, maybe there's some additional then rules follow. Or you could be faced with a set of rules. If a Y winding exists, select the Y side as the phase reference. So in other words, if we have a Y delta transformer, then we need to select the Y side, which is the winding 1 side. If it's a delta Y transformer, then we need to select the winding 2 side. Okay, and then the appropriate matrix for the other equations. So yeah, we have two different approaches. One set of rules is telling you to go one way, and another set of rules is telling you to go another way. Why should that be? Okay, so let's have a look a little bit further. So firstly, for all external faults or through load current, okay, for all cases, the calculated differential currents in all phases are 0. Okay, we're talking about faults through the transformer now, not internal faults, something that is passing through the transformer. So the differential current will be calculated as 0, irrespective of whether the winding 1 side or the winding 2 side is taken as the phase reference. Okay, so dig a little bit deeper on that. For any through fault or load condition, so long as the 87T function is properly set and there is no CT saturation, the assigned phase reference side, and by assigning the phase reference side means selecting what matrices will be used, it makes no difference, and the differential currents will be 0. However, the issue comes in for internal faults. Okay, so matrix selection, resulting from selection of which is the phase reference, comes into play more for internal faults, okay, because most of them are single phase, okay, as with most places on the network, and the calculated differential currents will be different for different matrix selections. Okay, so let's have a look at that. So here we have that same transformer we had earlier, the DYN1, okay. As far as the matrix equation setup is concerned, and I just made a fictitious transformer for this, and we placed a fault on the A phase of the secondary side, winding 2 side, and I just allowed 3 per unit in feed from the winding 1 side and 1 per unit in feed from the winding 2 side. Okay, so that's just totally fictitious to show a calculation. Okay, but so the winding 2 side matrix must subtract 0 sequence currents because it's a delta Y transformer, and remember on the Y side 0 sequence currents can flow which are trapped in this delta, so the Y side needs to have the 0 sequence subtraction. So if the delta side is selected as the phase reference, then remember the Y side currents, the winding 2 side currents must rotate anti-clockwise plus 30 degrees. Okay, so they have to go anti-clockwise. And if you choose the Y side as the phase reference, then of course the delta side currents need to get a 30-degree shift in the opposite direction. Okay, they need to go clockwise because now they have the delta side needs to line with the Y side. All right. So here I entered the values. So firstly, we look at the delta side selected as the phase reference. So this would be the selected matrix for that. And this would be the matrix that would need to be put on the Y side. Here are the primary currents. And if you make the calculation, you can see that we'd have equally large differential currents in two phases. And so the 87T would operate in both these phases. And also we can see that the calculated differential currents would not correspond to the limb of the fault because we would get equal currents in two phases. Now, if we look at the Y side as the phase reference, and just to point out, you can see that the currents are unchanged. What is changed is the selection of the phase reference side. So now the Y side is the phase reference side, okay, and the matrix looks like this because we've had to include the zero sequence subtraction, and here would be the required matrix to do the shift of the delta side currents. And if you look at this, you can see that now we have the highest current, differential current calculated for phase A, and then two half-size currents calculated for phase B and phase C. So you can see from this why you would get operation in three phases as opposed to just two phases like before. And you can also see that the differential current of the faulted phase is the highest. And so if you were looking at a disturbance record or something like that was showing the currents, you would get a clear indication actually that this fault has now occurred in phase A. So here's the comparison of the two. So remember the delta side, we had equal currents in A and C, okay? If we use the Y side as the phase reference, we had the highest current in phase A, lower currents or half currents in phases B and C, and also that the differential current in phase A is higher than the differential current measured when the delta side is as the phase reference, and it's higher by a factor of 1.155. And that comes from this here at the bottom right, which is really reflects back to the matrices that are used. So here's an actual example. This transformer exists. And what happened is, I won't go through the details of the whole transformer. It was an auto transformer. The D-winding is not used. It had so a two-winding differential, looking at winding 1 and winding 2. And what happened is, initially there was an external three-phase fault. Okay, so that is of not too much importance for us right now, but there was a three-phase external fault. And when that three-phase external fault cleared, you can see where the transition is. The three-phase fault, when it cleared, it actually became an internal C-phase fault. And we're going to be looking at the values, at the current values from winding 1 and winding 2 during the time of the internal C-phase fault, because this is the single-phase fault, and we're hoping to see similar information from a measured event than what my theoretical calculation showed. So now, because it's an auto transformer, we'll use the same matrix, left and right. And all we're doing is we're taking the recorded values, and through a tool that can make the calculations, we are we have programmed the matrix equation, and we are seeing what is the calculated differential current. So if you take the matrix, that will do a plus 30-degree shift, you can see we get equal differential current in 2 phases and nothing in the 3rd phase. And if you look at the scale, it sits somewhere just above the 60 here. If you take the matrix that does minus 30-degree rotate, you can see again we get differential current, equal differential current in 2 phases. The unfaulted phase has just been switched now with no current in the third, no differential current in the 3rd phase, and again the magnitude is about what we would expect. If we take the 0-degree matrix, and this is essentially the matrix that would make a Y winding the phase reference, okay, and because it's an auto transformer with a delta tertiary, we have to use the form of that subtracts the 0 sequence. But now you can see we get the highest differential current in the faulted phase, which is phase C. We get half the current in phases B and C. And if you look at the magnitude of phase C, you can see it sits somewhere just 75 or something on that percentage line. And so you can see that the differential current in phase C here was actually a little bit bigger than what was measured when we got the 2 equal differential currents using a matrix that would effectively be the same as using the delta side as the phase reference. Okay, so we've looked at the calculation of the differential current now, but let's just look a little bit at the impact of the restraint current calculation. So there are a number of methods that are frequently encountered. One of them is that the restraint current in all 3 phases will be equal. And if we look at what we call those compensated currents, okay, and if we've got a 2-winding transformer, there will be 6 of them. And what it does, and remember, the compensated current has already undergone the magnitude compensation, so they've all been brought to the same level. And so we would choose which is the biggest current of those 6, and we would apply that as the restraint current for all 3 phases. Other methods would be for instance, for phase A, to take the compensated current for phase A, winding 1 plus winding 2. For phase B, it would be also winding 1 plus winding 2, but for phase B, and similarly for phase C. And then another method may be to take the same as method 2, but have a divide by 2 factor. So now what I have here is I have an external phase-to-phase fault, okay, on the same transformer, external phase-to-phase fault on the winding 2 side. Okay, so you can see, you know, and the fault is BC, so these are the winding 2 side currents there on the right, and calculated the same currents for, well, the requisite currents for that would be flowing on the winding 1 side. And with the delta winding as the phase reference, if you look at the matrix on the winding 1 side, that would give you the delta winding as the phase reference. So when we calculate the compensated currents, you can see now in each phase, if you had to add them, they would sum to 0, and that would be what we would expect because it's an external fault. But if we now look at the calculation of the restraint quantities, you can see that for method 1, which is using the it's looking at the maximum current and it's applying that to phases A, B, and C. So if we look at those 6 compensated currents, you can see obviously that the 1004.1 is the maximum, and so that would be the chosen restraint current for all 3 phases. If we look at method 2, this would be, the 502 plus 502 for phase A, the 104.1 plus 104.1 for phase B, and similarly for phase C. And so you can see that this is how the compensated currents, or the restraint current, would be calculated if we use method 2. Now, what we have here is exactly the same fault, exactly the same current. So if you look at the winding 1 and winding 2 side measured currents, it's exactly the same. It's exactly the same here. All we've done differently is we've had the Y winding selected as the phase reference. Okay, but again, because it's a delta Y transformer, the matrix used on the Y side needs to have the zero sequence subtraction. And then we have the requisite matrix on the delta side. And again, if you look there, okay, it's an external fault, and if you sum the compensated currents for each phase, you will see that the calculated differential current would be 0. And right, so now let's look at the calculation of the restraint current. So if you're using method 1, okay, you would look at those 6 currents and say, well, okay, there's theoretically 4 of them the same, but that would be the chosen restraint value, and that would be applied to phases A, B, and C. If we looked at method 2, okay, you would see for phase A, it would actually calculate theoretically, for the theoretical calculation, it would calculate 0. And for phases B and C, okay, it would be the 869 plus 869, and so you get that value of 1739. So let's have a look and see how that looks actually on a characteristic. So first of all, if we're looking at let's look at the delta winding as phase reference. Now, this will go back quickly here. All right, so remember when we had the delta winding as the phase reference, method 1 and method 2A and C calculated the same restraint quantity, but method 2B calculated a quantity that was double. So if we look at this, if we look here, you'll see that over here, this is method 1, ABC, and method 2A and C would put you here on the x-axis, and for method 2B would put you at the 8 per unit point. If we go back and look here, when we had the Y winding as the phase reference, then you can see that for method 1, okay, all 3 phases would be calculated the same. And for method 2, we would have 0 for phase A, and phase B and C would be the same. So if we come here, you can see for method 1, here we would be at the 3.4 something would be ABC for method 1. We were just under 7 for method 2, B and C, but we were 0 for method 2A. Okay, so all we've done here is we've taken exactly the same external fault, and we've seen, based on how the restraint current is calculated, where the restraint current would be on the x-axis for delta side used as phase reference versus Y side used as phase reference. So how does that impact us going forward? Well, for this BC fault, okay, if we had the delta winding as the phase reference, remember the delta winding as the phase reference would give us the restraint current sitting at 4 per unit, and for for method 2, phase B at 8 per unit. But for the delta winding as phase reference, both methods 1 and 2 would calculate sufficient restraint current such that for this external B to C fault, it would ensure stability. Okay, because remember the characteristic, we are, in the part of the characteristic where the characteristic is increasing, and so we would get sufficient stability should there be some measurement error or something like that going on, some small amount of CT saturation. We would have sufficient margin to have stability. If we look at the Y winding as the phase reference, so if we go back here and see, if we are using method 1, okay, you'll see where the restraint current ABC is plotted. So there will be, the curve is already into the second slope at this particular location. So again, for some small amount of error, we would have sufficient restraint such that we would get stability. But the problem is, what about method 2, where the restraint value for A phase was measured, was calculated theoretically as 0. So now, if due to some CT error, okay, a differential current would be calculated for phase A, okay, which would also have a very small calculated restraint current, as we've seen, theoretically 0, when using method 2. So this could give a potential unwanted operation for the external face-to-face fault. Okay, so we've calculated very, very small restraint, and so we're in the most, even if it was some small value, not exactly 0, we're in the most sensitive part of the characteristic. So a small amount of differential current could then potentially go into the operate area, and we could get a misoperation. And such a small amount of differential current could be due, for instance, due to some small CT error or something like that. So what can we say then for selection of phase reference? If we are using method 2 for calculating the restraint currents, then we really need to select the delta side as the phase reference, because if we choose the Y side as the phase reference, we could potentially have a problem. So method 2 for calculating the restraint currents really means we should select the delta side as the phase reference. If we use method 1 for calculating the restraint currents, then we can select either the Y or the delta side as the phase reference, because again, if we go back here, okay, so the Y side is phase reference. So if we're looking at calculating the restraint currents with method 1, then we would have sufficient restraint current. So if method 1 for calculating the restraint currents, then we can select either the Y or the delta side as the phase reference. All right. So is there a better choice to go Y or delta? Well, if you choose the Y side, there are certain benefits, okay, that maybe can be taken advantage of. Firstly, you can see that we would have slightly increased sensitivity for internal single-phase faults, because remember, if the Y side was was taken as the phase reference, then the maximum differential current would be calculated in one phase, and that differential current would be a little bit bigger by that factor of 1.155 over the currents calculated if the delta side was taken as the phase reference. So by having slightly higher differential current calculated, okay, you have slightly increased sensitivity. You get a more definite indication of the actual limb of the magnetic core where the fault occurred. And so remember that even though the relay may have operated now in 3 phases, okay, if you had to look at a disturbance record or something like that, you would see clearly the phase that had the fault. Whereas with the delta side as the phase reference, it would operate in 2 phases. And if you looked at a disturbance record, you would see that those 2 phases would have essentially the same amount of current. So what can we say then by way of a conclusion? Okay, and remember the expectations that we started with, okay, that you have the utility protection engineer, because of the policy of his company, you need to have system A, system B, and to avoid the common mode errors, potential common mode errors, you want to have system A different from system B. Okay. So can the protection engineer, can the settings engineer have the expectation that these 2 relays will have the same settings? No. Okay. You would have to look at the, what the manufacturer is saying, and based on, in particular, how the restraint current is being calculated, there would be those rules defined. Operate identically. Well, I made this a lighter color, and the only reason why I really bring this one up is because when I say operate identically, because we know that if you select the Y side as the phase reference, you do have slightly better sensitivity because the calculated differential current is a bit higher. So essentially, the expectation is that the relay would operate for the fault, but you could have slightly better sensitivity when you select the Y side as the phase reference. And will the relay report the same target indications for the same fault? And there it's no, because you can see if you chose the delta side as the phase reference, you would get 2 phases operating, where if you chose the Y side as the phase reference, you would get 3 phase operating. So the same best practice application rules and setting guidelines are no longer applied generally for microprocessor-based 87T functions, because you see it was kind of standard practice before with the pre-microprocessor generation that you'd have the delta Y transformer. The delta side would be the phase reference. The Y side, you would have the delta connection of the CT, and that's how you would do it. But now with a microprocessor-based relay, you have other options, but just to bear in mind that the same rules and setting guidelines no longer generally apply. So there's no best fits all common setting rules, okay, as each 87T function has its own setting rules to follow. And really for the protection engineer, for the settings engineer, knowing, understanding, and following these, okay, is the key to achieving the best performance. So this is the end of my presentation. Monica, I gave you a few minutes.
Thank you very much, Mike. We have a couple of questions coming up here. Let's try to answer them, and then if any unanswered question, we will send out your replies as a follow-up. I can see a question from Alex. How do you calculate the ID mean?
Okay. So I can't speak for other relay manufacturers, but mostly our default value, okay, through years of experience, and that default value is 30%. So through years of experience has shown to be a good value. But there are some things to consider. The first thing is if the transformer has a tap changer, you need to be aware of what is the maximum tap in either direction, because as you tap, if you are not compensating for the tap position, as you tap, you are the magnitude conversion, if that is fixed for nominal tap, so that is fixed in the calculation. But as you tap, the currents, of course, are going to adjust according to the actual transformation ratio. So you have to be aware of what is the maximum or minimum tap positions, and potentially also be not only for conditions of load flow, but maybe even you've got to be if you have an external fault. So now you've got more current than load flowing through. So the error because of the fixed transformation ratio will get bigger. The differential current calculated will be more. So you've got to be a little bit cognizant of that. On the other hand, if you compensate for tap position, okay, such that each time the transformer taps, okay, the relay becomes aware of what is the tap position and what is the new transformation ratio, and can introduce or put that into the calculation. So the calculation, the magnitude compensation ratio in the calculation actually becomes a function of tap position. Then of course you can potentially have a more sensitive setting, because each time you tap, it should compensate. But if you do that, you just have to take the extra precaution that for some reason, the method used for informing the relay what is the tap position, that could fail. Something could go wrong in that feedback. And so you need to implement means to recognize that has happened. And as soon as that happens, okay, and now the function will realize, hey, I don't know what tap position I'm at anymore. I have a relatively sensitive setting, but because I don't know what is tap position anymore, I have to automatically desensitize. So, yeah, hopefully that was the answer you were hoping for.
Thank you, Mike. And the other question is from Norik Mikoyan. Is transformer 87T different from 87G applied for generator protection?
Yes, because with 87, you see the generator, you have the CT at the one side of the generator, and you have a CT on the other side, and there's a fixed piece of metal, the winding of the generator, the stator winding of the generator. With a transformer, the two windings are actually magnetically coupled, and so what that means then is that and the generator always the phase A current that you measure on the neutral side and is the phase A current, as I said, with a galvanically connection piece of metal between. Whereas the transformer, it's not like that. So the transformer, you have a whole lot of extra things to take care of. And those are the things like, what is the transformation ratio? Because that adjusts, as I said through the presentation, even if you've got just balanced current flowing, the current flowing in and the current flowing out is going to have an unequal magnitude, which you won't have on a generator. The current flowing in and the current flowing out could have a different phase angle, which you won't have on a generator. The current on one side could see zero sequence and not on the other side for a transformer, which you wouldn't see on a generator. So, yeah, the generator 87G and the 87T do have to take care of a number of different things.
Thank you, Mike. And another question is from Evelyn. Do you restricted ground fault protection as a positive complement to 87T?
Sorry, Monica, I missed that.
Yes, if you can look at your Q&A screen.
Oh, okay.
You will see the question there. The first question from Evelyn. Thank you.
But I think it had something to do with the 87N, right? I don't know where.
Yes.
Yes. So, okay. So, the thing is this, with 87T, okay, there is, I mean, it is a sensitive protection, and these days, they, you know, with the microprocessor-based relays, you know, we've added extra functionality like the negative sequence part and things like that. So at the end of the day, you've improved the sensitivity of the composite, shall we say, 87T function, but it's still quite normal, I would think, at least in my experience before coming to the U.S. The U.S. seemed to be a little bit not so common here, but certainly what I am used to, it was relatively common to include 87N or the restricted earth faults, and the idea is that with the restricted earth fault, you could, for ground faults that occur near the Y point or the start point of the winding, that may be a little bit, get to be a little bit outside the sensitivity of the 87T, then potentially the 87N would see that and it would complement the 87T.
Thank you, Mike. And another and the last question for today will be 87T is primary protection. Is it really necessary to apply duplicate 87T from different vendor when other backup protections are applied?
That's really the decision of the protection philosophy of the utility. But normally when you get to transmission level sizes, that is done because you know, when you have an internal fault, particularly, you know, the zone of protection actually extends a little bit outside the transformer as well. But if you have an internal fault, the sooner you get that fault cleared, the better. Because the transformer, you know, is a very expensive device, so that, you know, the more you limit the damage, the better. But that's not the only reason. It's that if that fault stays on just a little bit longer than necessary, you could face a lot of other things like tank rupture. You could face ignition of the oil. You could face a number of other things that would then actually be quite significant, rather than just a transformer that is now faulted and needs repair. So, I mean, I've actually seen a substation where the transformer caught fire. It burned for like 3 days, and the rest of the substation was twisted metal. So, yeah, you would want to get rid of that fault as soon as possible. And I would say for transmission level transformers, definitely it makes sense to put a system A and a system B. Whether system A and system B have to be different, well, that's now a different philosophical discussion. But the fact that you had two equal operating system A and system B, I think is quite, if I was working in a utility, I would do that.
Thank you, Mike. So this was all for today, and I would like to inform everybody that certificates, whoever watched the webinar 40 minutes, those certificates will be sent to you as a follow-up by your email. Thank you very much. And I would like to thank again, Mike, for your great presentation. And I wish everyone to stay safe and have a great rest of the day. Thanks again, and goodbye.
And from me, thank you, everybody, for listening. I really appreciate it.